Okay, we're going to move on to dealing with arc length and surface area, so the integral calculus side of parametrics. In the last couple of videos, we talked about derivative calculus, differential calculus in terms of parametrics, dealing with first and second derivative, equations of tangent lines, intervals of concavity. But here's where it actually gets a little bit fun. Now remember when we were dealing with arc length and surface area with respect to functions. This was section 8.1 in your book, and this was section 8.2. We dealt with, and I even constructed the whole thing for arc length. Let's go ahead and do arc length first, but of course they're related, and we see, of course, right here the arc length piece of surface area when it's being evaluated, and we're going to have that piece in the parametric as well. So let's actually show where the formula for arc length comes from in parametric, and we're going to of course start with this. But instead of dy dx, I'm going to change that into dy dt over dx dt squared. Okay, and then I'm going to change dx into dx dt times dt. All of this is in an effort to transform it, okay, into something with respect to dt. Now, I know that I'm going to be integrating with respect to t. A and b no longer make any sense anymore. We'll call these alpha and beta and just know that they'll refer to t values rather than x values. Okay. Now what I'm going to do now is I'm going to do that, okay, so that I can actually use properties of radicals and actually multiply that into this radicand and transform it. And so I'm going to get alpha to beta, and when I distribute it to the first one, it's just multiplied by 1, so it just becomes that. When I distribute it to this second term right here, it's going to get rid of the denominator, and you have dy dt squared times dt. Or if you want, since I just introduced sort of the x prime and y prime, if you want to clean it up just a little bit, this is x prime squared, and that's y prime squared dt. That is the formula for finding arc length using parametrics, okay? So let's go ahead, we're going to do two examples where we're merely setting it up, and then we're actually going to try and actually do one and evaluate it, okay? The first one we're going to look at is going to be x 3t minus t squared, and y is equal to 2t to the 3 halves. And we want the arc length between 1 and 3. Okay? So it gives us our limits of integration. That's nice. We know that x prime is going to be 3 minus 2t. We know that y prime is going to be 3t to the 1 half, or 3 root t. So all we have to do is we just have to say, well, arc length is going to be alpha to beta of the square root of x prime squared plus y prime squared dt. And that's easy enough, right? And, you know, if we're asked to do that by hand, it would probably be a little bit, you know, I mean, the radicals are a little bit messy. And some of these will have to be done by the calculator because the calculator is the only one that's actually capable of doing it. Some of these, because there's a nasty multi-term thing under a radical, if you actually can do them by hand, that's where the whole trig sub stuff comes in. Trig sub winds up being very, very helpful in order to simplify multi-term radicands, right? Transform them using your Pythagorean IDs. Okay, let's go ahead and do another one. Let's go ahead and do x is equal to t plus sine t, and y is equal to t minus cosine t. Let's go ahead and take those derivatives. By the way, it's going to be from 0 to pi. They want the mythic they. X of t is going to be 1 plus cosine t, and y prime of t is going to be 1 plus sine t. The arc length, oh sorry, forgot to move that up, but we see here the interval. This is the original parametric, and these are the derivatives. Okay, obviously that changes sign right there because the derivative of cosine is negative sine. And so we simply have to set it up, limits of integration, alpha to beta, square root of 1 plus cosine t, that's x prime, squared, 1 plus sine t, that's y prime, squared, and then dt. And this one, you would have, if it is integrable, that would involve a whole lot of trig IDs and multiplying it out and transforming stuff using your IDs and whatnot. I'm not actually sure whether it actually can be done, but you know, you could play around with it if your curiosity is getting the best of you. What I'd like to do right now is I'd like to turn our attention to one that we can actually execute, actually evaluate. Okay. How about x is equal to 6t squared and y is equal to 2t cubed, and the interval that I'm interested in is 1 to 4. Well, I know that x prime is going to be 12t. I know that y prime is going to be 6t squared. And so my arc length, 1 to 4, is 12t squared plus 6t squared. Okay, I'm going to go 1 to 4, and let's go ahead and see the way this works out. This is going to be 144t squared plus 36t to the 4th dt. Now I know that 36 actually does go into 144. It goes in 4 times. So underneath this radical, I actually can do a little bit of factoring. Okay. So we have 36t squared 4 plus t squared dt. In simplifying, that can be pulled out, right? And we actually wind up, and we know that we can actually pull it out and not have to use absolute value bars because we're interested in positive values of t. So you go 1 to 4 of 6t t squared plus 4 dt, if you want to turn it back into descending order. And now this can just be done by regular u sub. Okay, u is equal to t squared plus 4. du is 2t dt. So we'll change this 6 into a 2 and pull 3 outside. Remember, this is a definite integral using u sub. So if t is equal to 1, u is going to be equal to 5, because you plug in 1 squared plus 4 is 5. Plug in a 4 right here. 4 squared is 16 plus 4 is 20. So the changes in the limits of integration wind up being rather straightforward once you actually change it. Okay, sorry, I shouldn't have changed it yet. I should have changed the limits on the next round, but since I've already done it, let's go ahead and leave it like that. You get u to the 1/2 du, which becomes 2/3 u to the 3/2 from 5 to 20, and of course that's going to be some sort of fraction. It's going to be some sort of irrational number based upon the fact that you're going to be taking the square root of 5. But from here you ought to be able to sort of move forward from there. Okay, let's go ahead and I'll tell you what. Let's at least set up one more of these so that we're good on arc length before we move on. And let's do one that's a little bit nasty, just for the sake of doing one that's nasty. How about x is equal to arc sine t, and I can hear you groaning already, and natural log square root of 1 minus t squared. Okay, now here's the thing. This y right here looks pretty nasty. Oh, by the way, we're going from 0 to 1/2. That's going to be our... Okay, I want you to stop and I want you to think very, very quickly about why this is not actually a nasty y. Okay, because that is actually the natural log of 1 minus t squared to the 1/2, or 1/2 natural log 1 minus t squared. And actually, since that factors, I actually could use rules of exponents, I mean properties of logarithms, same thing anyway, to actually split that up even further. But I'm not going to. I'm going to leave it like that because I want to leave it in a single rational expression. So let's go ahead and do x prime. X prime is 1 over the square root of 1 minus t squared, and y prime is going to be 1/2 times negative 2t over 1 minus t squared. Okay, that 2 right there cancels out with that 2 right there. You can go ahead and, it doesn't really matter, let's just go ahead and leave it like this. This winds up being negative t over 1 minus t squared. We're just going to set it up. We're not going to evaluate it, so we don't have to actually think ahead of time as to what form of those would be best when I start simplifying the radicand. So I know that my arc length is going to run from 0 to 1/2, and I simply have to do 1 over the square root of 1 minus t squared squared, and then negative t, 1 minus t squared squared, and that winds up being my integral right there. Okay. In the next video, we'll fold this in, because of course arc length has everything to, basically as a constituent part of surface area and its formula. And I'll remind you kind of how that works, and then we'll move on to do some examples of those. As always, email me with any questions that you have. Bye.